Today we're diving into three essential qualities of good software: correctness, robustness, and efficiency. These principles guide us toward writing code that not only works, but works well, reliably, and performs as expected under different conditions. Correctness is our baseline. It's about ensuring our code does exactly what it's supposed to do. Correctness focuses on accuracy and functionality. Without it, our program simply won't deliver the intended outcomes. Robustness takes this a step further by preparing our code to handle unexpected or adverse situations. Robust programs handle edge cases and errors gracefully rather than crashing or producing faulty results when things don't go as planned. Finally, we have efficiency, which is all about resource management. Efficient code performs tasks quickly and uses resources like memory and CPU responsibly, making our programs responsible and scalable. Each of these concepts play a crucial role in building quality software. As we go through this chapter, we'll explore practical techniques to incorporate all three into our code, making our programs not only correct, but also robust and efficient. First up, we have ensuring software quality in Java. That means we build programs that are correct, robust, and efficient. We understand how Java handles errors and exceptions, and we implement best practices for input validation, error handling, and efficiency. Correctness means the program performs its intended tasks accurately, and robustness means the program handles unexpected or invalid input without crashing. Some horror stories. There are some famous software failures. The Ariane 5 rocket explosion, which was caused by integer overflow. The Mars Climate Orbiter loss, which was a unit mismatch, metric versus imperial. And healthcare system bugs, which are incorrect dosages due to calculation errors. So the takeaway is critical importance of correct and robust code to prevent catastrophic errors. Java's strong typing and error handling. So strong typing reduces type-related errors, and strong typing in Java means that each variable, parameter, and expression has a defined type, and that type determines how it can be used. Garbage collection helps prevent memory leaks, and checked exceptions promotes proactive error management. Java's design principles help prevent common sources of software failures. There are still problems in Java, so there's limitations in error handling, unchecked exceptions like null pointer exceptions, index out of bounds exceptions, etc. Memory leaks, possible if resources aren't properly closed, and concurrency challenges, potential race conditions, and multi-threading. So while Java mitigates many issues, careful programming is still essential. So writing correct programs. The goal is ensuring programs behave correctly under all expected conditions. Some strategies would be using mathematical and logical tools to analyze program correctness and define clear preconditions, postconditions, and invariants. Provably correct programs. These are programs proven to meet all specifications using formal methods. Some practical examples are common in critical systems like aerospace and medical, and limited in everyday programming due to complexity. Preconditions and postconditions. Preconditions are assumptions about method parameters before execution. For example, a square root function, the input must be non-negative. Postconditions, expected outcomes after method execution. An example would be a search function should return a valid index or indicate failure. The purpose of this is to document expectations and results, aiding readability and debugging. Invariants are conditions that remain true during the program's execution. For example, in a sorted array, elements are always in ascending order. This is important. It helps us in understanding code by defining fixed rules and allows early detection of logical errors during testing. Robust handling of input. Input validation. So first, filter and sanitize input to avoid unexpected behavior. There are different types of input handling, like data type checks, which ensure values are compatible. Range checks prevent values outside acceptable bounds. And format checks use regular expressions for specific formats. You should implement validation as early as possible in your code. Exceptions and try-catch. The purpose of exceptions: error notification. Exceptions signal errors in program execution, and error recovery allows safe handling of errors. And then types of exceptions. We have checked exceptions, which require handling like our IO exceptions, and unchecked exceptions, which are optional handling like null pointer exceptions. Java exception hierarchy. So we have throwable, which is the base class for all exceptions. Error, which represents serious issues like an out-of-memory error. Exception, recoverable issues like IO exception. And runtime exception, common unchecked exceptions. Then there are custom exceptions, which define specialized exception classes for clearer error handling. Here's an example of the try statement. This is the try-catch structure. The try block of code may throw an exception, and the catch block handles the exceptions thrown into thrown in the try block. Throwing custom exceptions. Use the throw keyword to signal an error in your code. The purpose of this is to improve clarity by throwing meaningful exceptions when invalid situations occur. You can see in this example, this is a custom thrown exception. Mandatory exception handling. So some checked exceptions, they must be declared in method signatures with throws, and it forces programmers to handle exceptions, reducing error risk. So mandatory exception handling is a key feature in Java's approach to error management. It ensures certain types of errors are always checked and addressed by the developer. And then we have programming with exceptions. Some best practices: catch only necessary exceptions, avoid catch-all. Ensure resources like files are closed properly. Use try with resources. Document exception handling so users know potential risks. Now we're going to go through some examples. First, we are going to do a compile time error in Java. Okay, so here we can see we have an error that we get on compile time that says incompatible type, Java lang string cannot be converted to int. So this is because we have quotation marks around the 5, which in Java shows it, interprets it as a string. So let's do a couple examples of provably correct programs. So in software engineering, provable correctness means using formal methods to ensure a program meets its specifications. This often involves logic and mathematical proofs, but we can also use assertions for simple checks. Formal verification tools are typically used here. Okay, so we see for this we get result 5, and then for the second one we get an exception telling us we cannot divide by 0. So this program is provably correct when it can be shown to meet its specification under all valid inputs. The precondition check, so the assertion ensures that a critical precondition, the denominator must not be 0, is met before the division operation. This precondition is essential because dividing by 0 is undefined. So given that the precondition holds, the denominator is non-zero, the method guarantees to return the correct integer result of the division without errors or unexpected behavior. And then provable termination and safety, the method either returns the correct division result when the precondition is satisfied or throws an assertion error if the precondition is violated, which stops further execution and prevents undefined behavior. So let's do another example of provably correct. We need to turn on assertions for this, so we will do this. Okay, so now we see the exception is thrown. We have an assertion error. So because we have this assert here, it's not even getting to this error message at the bottom. Let's try. Okay, here we see our assertion error. So here the assertions ensure that the preconditions n greater than or equal to 0 and that the result remains valid. Result is greater than 0. Assertions help validate correctness by checking the assumptions in the code. Next, we will move on to pre and post conditions. So preconditions are conditions that must be true before a method executes, and post conditions are conditions that must be true after a method completes. All right, let's change the name of this. So here we see square root of 25 is 5, and then in the second case we throw the exception and we see the number must be non-negative. So again, the precondition is the method checks if the input number is non-negative. If the number is negative, it throws an illegal argument exception, which we see here with the message number must be non-negative. Square root calculation, it uses math.square root to compute the square root, then cast the result to the int. And then the postcondition. The postcondition is that the square of the result must be less than or equal to the original number. The assertion assert result times result less than equal to number verifies the condition after the calculation. And if the input is negative, the exception is thrown. And in the case of an invalid postcondition, like a floating point or rounding errors or other issues, the program will throw an assertion error with the message postcondition failed. Okay, let's do another example. Okay, so here the bank account class contains a private field. Let's scroll up a bit. Balance, which represents the current balance of the account. The constructor bank account ensures that the initial balance is not negative. Then we have a withdraw method. The preconditions, so before performing the withdrawal, the method checks if the amount is greater than 0, it must be positive, and if the amount is less than or equal to the current balance, ensuring there are sufficient funds. If any of the conditions are violated, an illegal argument exception is thrown with an appropriate message. If the preconditions are met, the amount is subtracted from the balance. And then our post condition, the method uses an assert statement to ensure that the balance is non-negative after the withdrawal. If the balance becomes negative, an assertion error will be thrown. We then have the get balance method. This method returns the current balance of the account. And in our main method, we create a bank account object with an initial balance of $1,000. It demonstrates a valid withdrawal of 200, which reduces the balance, and then it demonstrates invalid withdrawals, one with a negative amount and one with an argument greater than the balance. And then we have one that reduces the balance to 0. Here the method checks the precondition amount greater than 0 and amount less than or equal to the balance, and the post condition ensured by assert confirms that the balance stays valid after withdrawal. And here we can see the results. Amount must be positive, insufficient funds, and our 0 balance at the end. Next, we're going to change this bank account a little bit to do an example of an invariant. An invariant is a condition that should always hold true during an object's life cycle or within a loop. So let's just change this a bit. We'll leave that, and we'll get rid of these methods. Okay, so we can see our current balance is $120 after depositing 50 and withdrawing 30. In this code, the primary invariant is that the balance of the account must never be negative. This invariant is an essential rule that helps ensure the integrity of the bank account object, making sure the account balance remains valid under all conditions. So when an object of the bank account class is created, the bank account constructor is called. This constructor checks that the initial balance is non-negative. If the initial balance is negative, the constructor throws the illegal argument exception, ensuring that the account starts with a valid balance and prevents the invariant from being violated from the very beginning. Then we have our deposit method, which allows money to be deposited into the account. The method checks that the amount being deposited is positive, and if the deposit amount is negative, an illegal argument is thrown. And then this method, the deposit method, does not explicitly check the invariant because the deposit logic ensures that the balance remains non-negative. It does indirectly contribute to maintaining the invariant by only allowing positive deposits. And then the withdrawal method allows money to be withdrawn from the account before the withdrawal is made. It checks two conditions. The amount must be positive and the amount must be less than or equal to the current balance. You cannot withdraw more than what is available to the account. So this method enforces the invariant by preventing a withdrawal that would result in a negative balance. If you try to withdraw more than the available balance, the withdrawal is rejected, ensuring that the balance stays non-negative. So the balance of the bank account is the key aspect of this invariant, and the code ensures that at no point will the balance go below zero. So the two primary mechanisms for maintaining this invariant are the constructor, which ensures that the initial balance is valid and non-negative, and the withdrawal method, which prevents withdrawals that would cause the balance to be negative. So this demonstrates invariance by ensuring that the balance always remains non-negative. Okay, let's do another invariant example. Okay, so here is sorted checks the invariant that the list remains sorted after every insertion. This ensures that the main property of sorted list holds true without. I'm sorry, throughout. So the invariant is that the list numbers must always remain sorted after each insertion. And this is the rule or condition that the class guarantees for its internal state. Next, we are going to do robust handling of output. Okay, now let's try with some invalid. So our regex allowed for this, so let's add a little bit more to this. There we go. So this is an example of handling robust inputs. This is a basic implementation for validating an email address format. We changed the regex. The new pattern ensures at least one period in the domain, which we could see the initial run johndoe@com worked just fine, but with the new regex in place, it fails. So the regular expression ensures that a proper top-level domain is present after the domain name. So a period followed by at least 2 alphabetic characters, such as .com or .org. And then the program will reject any input that doesn't conform to a more realistic email format, such as a domain without a period or an incomplete top-level domain. Let's do one more. Okay, so let's stop our old program and run this. Let's start with 150. Age must be between 0 and 120. Let's try A. And then we see enter a valid age on repeat. So where, okay, let's try consuming the entire line of valid input. Nope. Okay. Had some bracket mix up. Okay, 150. So this code ensures that the user input is numeric and falls within a valid range and provides clear feedback if the input doesn't meet these conditions. By using hasNextInt to check for valid integer input and clearing the invalid input with scanner.nextLine, the program avoids common issues like infinite loops and program crashes due to unexpected input. So this is another example of robust input handling. Next, we're doing an example of exceptions and exception classes. Creating custom exception classes allows better clarity when dealing with specific errors. So let's change this. So this custom exception, invalid age exception, provides a clear error message specific to the context of age validation, which is more informative than just a general exception. We can do one more example of this. So this class extends exception and is used to signal that the grade entered is outside the valid range of 0 to 100. That would be our invalid grade exception class. Our validate grade method checks if the given grade is within the range 0 to 100. If it's outside the range, it throws the custom exception, invalid grade exception. In our main method, the scanner is used to accept user input, and the program continuously prompts the user to enter a valid grade. The validate grade method is called inside a try block, and if the grade is invalid, an exception is thrown and caught by the catch block. The program then prints the error message and asks for a new input. If the input is valid, the program prints the grade and exits the loop. So this was another example of exceptions and creating custom exception classes. Next, let's do an example of a try statement. So here the try block allows each string to be parsed individually, with the catch block handling invalid formats and allowing the loop to continue. So we can see it does parse the numbers, and for values that are not valid numbers, we do get the invalid number format. Okay, we're going to do one more example. Here, the try-block catches array index out of bounds exceptions and allows the program to handle it gracefully without crashing. Next, we're going to do a couple examples of mandatory exception handling. Java requires certain exceptions to either be caught or declared, like IO exception. Okay, example.txt does not exist, so here the IO exception is a checked exception, so it must be either caught with the try catch or declared in the method signature, which is the throws IO exception. Okay, let's do another. Okay, so here handling the checked IO exception is mandatory because it ensures that if the file is missing or unreadable, the program provides feedback without terminating abruptly, which we can see here. We're going to do one more example of programming with exceptions. So this approach demonstrates effective exception handling by retrying the operation and providing clear feedback to the user on each attempt. So in this, the method connect takes two arguments, host and port, and the retry logic allows up to 3 attempts. And if a connection is successful, no IO exception is thrown. It prints a success message, closes the socket, and exits the loop. That's where the break is. If an IO exception occurs, the server is unreachable, the catch block increments the attempts counter and prints a failure message. If after 3 attempts the connection has not been established, a final message is printed to indicate that the program failed to connect after 3 attempts. So this was our lecture on Chapter 8, Section 8.1 to 8.3. If you have any questions, please send me an email.